Greetings, everyone. All right, well, let me just make sure everything is up and running. And here we go. Just want to make sure my audio works. Good. Okay, so the audio is working. Anyway, we are continuing from where I left off last time. Right. Okay, so doing book of proof here. All right. Okay. We are in So as I get further and further into this, I'm going to take probably longer times to focus on what's going on. Well, I did read, by the way, real quick, this is Book of Proof. Description is in the, download it in the description. It's free. It's Creative Commons. Download the book or buy it. It's a very nice book. Support the author. Put it on your bookshelf. People will think you're smart because you put a math book on your shelf. Just do it. Get the book. Won't regret it. It's got a lot of funny and smart asides inside it, so it's pretty cool. Now check the description. I don't get any kickbacks. This is one of my assigned books at Westchester University. I'm not in class right now, actually. I failed this class because I had to focus on work, so I'm working on my own time. I run a landscaping / handyman business. So now I am studying up. I'm going to take it when the next semester starts. All right. Right. So last time, if you were here last time, was Venn diagrams. This is a simpler way of doing it instead of constantly drawing a Venn diagram. Because let's say you had like 6 or 7 sets. And again, with a Venn diagram, like this is, you can put different items. It's not just like the whole of that set. Like as in a Venn diagram. So this is much more convenient. So I'm just writing a series of sets right here that we're going to be using to answer this question. The subscript refers to just a different set. So it's like these are all within the set A, but except I describe this. If I want to get technical here. Okay, hang on a minute. So these are called index sets. So the subscript, so we have A1, A2, A3, that's a subscript when you put on the bottom, and these are subscript sets. All right, okay. I am a landscaper and handyman. I'm not a math teacher. Bear that in mind. I make a lot of mistakes, and I Leroy Jenkins this. Nothing's prepared. I simply study the text and then do the questions and do the best I can. It makes it far more interesting, I think. All right. Let's see here. Let's okay. All right. I just came back from teaching skating. I teach it twice a week. So yeah, my students did well. All right. So here we go. We want to have the union of AI. And we're on section 1.8, page 29. But if you need a reference, you can go back and look at their examples. A good one is going to be on page 25. I'm just quickly referencing it here. So yeah, okay, so right. So we're just going to create a new set, and everything that's in common. Let's see, they all have A. A. What about B? They all have B. And they don't all have D. That's it. All right, so that's everything in common. And so remember what I said before, if you were here last time. So this is how I remember it. U is union. The N is intersection. So that's just a mental, really quick way to know which one is which. Union, intersection. I mean, at this point, I don't really need that, but it's a handy little thing to keep in the back of your head if you're ever confused or stressed on a test or whatever. Okay. I answered that incorrectly. Yeah, no, I'm an idiot. Okay, here we go. There, that's the intersection. The union, we're just going to combine all the sets. I'm glad I caught that. Okay, right. Okay, so there we go. That's the intersection, and the union would be A, B, C, D, E, F, G, H. Any I's? I don't think so. So that's the union. That means we take everything. We're not going to put two A's. It's because the same A. But in this case, we have between our four sets, we have A, B, we have a C and A2. A sub 2. D exists. Yes. E, F, G, and H is in A sub 4. Okay. And that's how you read a subscript. A sub 4. I tend to mumble and talk quickly. A sub 2. Right there. Okay. That's for subscript. So in this case, we have the okay. Okay, so this is similar to sigma notation, as you can see. It's very much like sigma notation, which is sigma notation is like this. And Ci equals 1 and A to the I, and then you list it. In this case, N being 4. So that's, I draw the worst sigmas. I can't draw a sigma. You know you're good at math when you can draw good sigmas and good curly braces. I'm not there yet. Okay. Yeah. Let's check out the answer. See if we're only doing the odds, so we don't damage the integrity of the book as a teaching tool. All right. Here we go. I believe it's, you can, here we go. 1.8 is on 296. All right, and I just try to cover my hand with the supposed A, B, C, D, E, F, G, H, A, and B. Okay, good. So I cover it with the subsequent answers with my hand so that I don't just like, give it away to myself. But you feel free to look in the back of the book and you could actually see if I'm doing anything correct or if, because I will make mistakes. Just keep that in mind. I am a student, not a teacher. All right. Okay. 3. Okay, I'm going to write this. For each n being a member of the natural set, let's an important word. It's an assignment word that we can use, and we can do that ourselves too. We could assign things to create a set. Like I've done it in previous streams where there's like a series of equations, but I wanted to work with them without having to constantly name the sequence of equations. I just wanted them in a box, so to speak. So I just said let C be defined as that equation, and that was it. And that's totally acceptable in math. It's just put them in a box. Okay. So for each n being a member of the natural set, let a sub n equal to 0 to n. So presumably from 0 to infinity. Okay, yeah, okay, that's fine. Let's see what the so that's just a statement. Union of a to the I. So hang on, let's see here. An I contains the natural sets. Okay, so for each n contains, so a to the n contain. So by the way, 0 is not part of the natural set. But in this case, I'm thinking what they want to do is they're asking what numbers do they all have in common, or in this case, I should say. Well, let's try this. So if we go for each n containing naturals, so n1. So if we say u, so let's try this. Say u. It needs to be bigger. Okay, a to the 1, which is equal to. I'm modifying it. I equals 1. So presumably it would be that entire set. And a to the 2. Yeah, I'm either going to get this right or wrong, but it seems to me that for each number containing the natural set, let a to the n, each set contains from 0 to infinity, positive infinity, which again, 0 is not part of the natural set, but it seems to me that the answer should be the union would be all of them. I would think. And the opposite, where do they intersect? Well, since each set contains exactly the same thing, I would say it's all of them, but I can get this wrong. So if I get this wrong, though, I'll figure it out. It's not a problem making mistakes. Being afraid of mistakes, that's a problem. Okay. All right. So, hold on a minute. I missed something. A3. So the first three. So the first three sets. So then that means I goes from 1 to 3. And yeah, hang on a minute. One to infinity to be a notion of the sets for a 1, 2, 3. So then we can write which is equal to I is 1, 2, 3, which is understood to be the union of the sets AI for I equal 1, 2, 3. Likewise, eighth, yes, equal to all of n I containing n. The I is a index set. All right. Well. I don't know. I'm thinking that as I read it, and this is the first three sets, a to the n goes to n. So the I just answered my own question. I think it goes something like this. So This is why you can't rush through this stuff. You got to take your time on math. It's not like when, we had to do like the times tables in school and a to the I equals 1. I think it's going to be like this. I could be wrong, but I think this is going to make, well, it certainly makes more sense mentally to me. So these are 3 sets, index sets. And then okay. So if we did that, this is going to make a whole lot more sense. So the union would be all of that, and their intersection is only going to be 0. No, are we supposed to list the empty set on this? It just lists the sets. No, I don't think so, because this isn't like we're not subdividing the sets. We're simply merging them or seeing what they all have. So there, as you could see. Okay. There. So there we go. For B, I see 0 and 1 appearing in set 1, 2, and 3. And I see 0, 1, 2, 3 would being the union. So the intersection, I would say it's 0, 1. Union would be 0, 1, 2, 3 for the sets. All right. At least I feel, even if I get this wrong, I feel like mentally it makes a lot more sense to me than what I was saying earlier. Okay. Wait a minute. Let's see here. Okay. 0. For B, I got B right, but I got A for each the n being a member of the natural set. Let A to the n go to n. Hold on. No, I answered it correctly but I wrote it incorrectly. Yes, that's what it is. Oh, okay, yeah. I pulled the 3 from the line above it for question 2. Okay, so yeah, I answered it correctly, but only because yeah. Hang on a minute. Yeah, I put that there, which we don't need. Okay. All right, so here's what's going on. I'm going to explain real quick. Right, so there is no limiter there. I made the mistake because I wrote it incorrectly, but I answered what I wrote correctly, which is promising. I'm learning something. So then we're going to say this, and I think that should be correct. 0 is not in the natural set. However, the answer would contain 0 as well as the natural set. So we're not limited. The n for us goes to infinity. It doesn't go to 3. But the examples I wrote below shows how this thing grows. it goes, the first set is going to contain 0, 1, second one 0, 1, 2, third set 0, 1, 2, 3, and so forth. It'll keep growing like that to infinity. But 0 and 1 will appear in every set. So the intersection is only 0 and 1. That, I believe, is going to be the corrected answer. Yeah, that's correct. Okay, so yeah, so A is corrected, B was correct. All right, so that's good. Like I said, I only got it wrong because I pulled the range from the question 2, which we weren't doing. We're just doing the odds. So in that sense, but that's good though, you know. All right, let's keep rolling. All right. Okay, and here we go. 1.8. All right, 5. See, this is why I'm doing this book, to retake this class. I mean, it's like it is so dense and there's so much math that you got to do if you want to do well, versus just kind of getting through and you're shell shocked at the end of it that you glad you survived, but you hardly remember anything. That's not what I want. I want to have, like, I want it all to be at my fingertips, all of it, all the math that I'm doing. I want to be able to pull it out, rearrange it, and use it whenever I need it. Okay. Right. Let's make sure I wrote it right. Let's start with there. That's always a good thing to start on. All right. So I contains the naturals, and then I contains the whole natural set. So let's just do first of all. We're gonna start writing sets. Union I is equal to a minute. Right. I'm gonna constrain them a little bit. Contains the natural set, and we're gonna just go with 1. We're just gonna get the first one in. All right, and then we're gonna say so then the set looks like this. It's gonna be, we take I, the first one is 1. It's gonna be 1 plus 1, which is 2. And that's the ordered pair there. Okay, let's try this. I contains naturals union 2 plus 1, which is equal to 2 plus limit. So the x position is 2, the y position is 3. These are closed ranges. Maybe I should graph this. All right. So then, but going to the n, to the nth degree, it's going to be, the union would be if I unite all the sets. So it's going to be, right, it's going to be infinity, positive infinity, and infinity. Because it's going to infinity, and infinity plus 1 is still infinity. And yeah, no, I think the union, but we're just adding the numbers. I believe we're just stacking them. We're not listing them. I think this is how it's going to be. I could be wrong. This is a hard chapter, as this is a somewhat different. I mean, like we've been doing stuff like this, but yeah, this is really pushing it. Okay, it is infinity on the second side, but it's only 1. Why is that only 1? I is a member of the naturals, and first one is Right. Yeah, I should correct this. It's another mistake. So, all right. This is infinity is unbounded. Okay. You can't have a closed infinity like this. Because where would you stop it? It's infinity. And this is 1. Why though? Actually, I would think it would be infinity, but it's the range probably. That's why. This, in other words, would be something like this. I think this is what they're getting at. So this is going to be 0, 1. This goes to infinity. Okay, I believe that's what they're getting at. So it's not an XY grid. This is simply ranges on a line. The first starts, and the thing is that the reason being, you want to the first one would represent the leftmost point, and the second would be the rightmost point. And in this case, because it's not an R2, that's why it's not on a grid. If this was an R2, it would probably be similar to. It would be a little different, but basically an R1 or an R, the one on the left, the X position would be the leftmost point, and it doesn't matter because so like the first one we could say goes to 1, 2, 3, 4, but at the same time that rolls into the second position, so we don't really need to worry about that. We just need to know the range. We don't care if the numbers overlap in it. Okay, I'm just gonna say hi. Geonormal Nito. Hi. Okay. Okay, there we go. All right, well, continuing on. Right, well, like I said in previous streams before, it's easy to get lost in math and make mistakes, but it's hard, very hard to stay lost if you just keep powering through it. Because the way math works is, if you are doing something wrong consistently, then your equations will break down. You'll consistently get wrong answers. So you're forced to work through it and figure out the correct answer, do research, whatnot. So, like for instance, I might say something that is perhaps not strictly ballroom. I might use the syntax, the lexicon of math idiosyncratically, which I know I do. Don't mean to sometimes, but I'm still just a student. But what I'm trying to say is that if I at least understand the process and get the right answers, then then I'm definitely on the right track, so to speak. And if I'm getting a wrong answer, I'm forced to get the right answer. Anyway, so that's what's great about math. You'll find your way out of at least at this level, just about any mess you get yourself in. As long as you study, though, if you don't crack open a textbook, it ain't gonna save you. All right, we're intersection. We're going to assume this is in R. Okay, in this case, so basically the line, it's in the natural line, but whatever. Yeah, we're going to assume this is the natural line. So what we're doing line, we're doing single dimension basically. We're going to range from I to I plus 1. These are close-ended. Now notice even though the top, both were closed brackets, because we're dealing with infinity, it's unbounded. So, where do they intersect? Well, if they all start at 1, well, how did they answer that for the first? How did I get? Okay, good. So, right, we're not printing sets here. We're printing coordinates. So, just gonna fix this. That was printing sets. We are printing coordinates. All right, so let's do this. All right, where do they intersect? Well, they all start at 1, and then 1, and they all will have 2 at least. So n to the 1. because if n is equal to 1, because natural start at 1, the first set would be 1, comma 2, closed. The second set would be 2, comma, wait a minute. Hold on. Oh, let's roll that. See what happens. 2, comma. I contains the naturals. 2, comma 3, and then it's going to be 3, comma 4. Where do they intersect? There might not be an intersection here. With the union, it's a little bit easier because it just adds everything up. But intersection, every output that we get whenever we pop from n has to be found in every other one in that specific slot, and I don't see that. So actually, I'm thinking it's just empty set or 0. I'm just gonna write empty set. Okay, this is a hard chapter. All right. Heyo, I got it. All right. That's good. Yeah, I was right. See, you got to write this stuff out. You can't just keep rolling it around in your head. Math doesn't really work if you're just like, you want to stare and think. You have to put pen to paper. You have to draw things out, and then you see things. All right. All right, and 7. All right, so 7 union of the reals cross multiplication I comma I plus 1, the closed set, and I contains the naturals. Okay. Oh. Okay, we're gonna say we're gonna range it to 1. Okay, let's see what we get here. We're gonna have the reals. The reals by 1, comma 2. Okay. I would say this would be negative infinity to infinity. But so if, let's say, the real is going to be, let's say, 1,000 times 1, it's 1,000 times 2 is 2,000. Negative 1,000, negative 1,000, negative 2,000. It would be, yeah, it would range. If it's R0, then it's 0, 0. Let's say it's negative infinity and infinity. And because these are infinities, we're going to keep them unbounded. Cannot contain infinity like that. At least at this juncture, we're just going to say that. Okay. So if I get this correct, I'm going to graph it. Let me see here. 7. Wait a minute. What am I doing? No, that's right. Hang on a minute. All right. So they want us to write it in set notation. Oh, right. Because we're cross multiplying now, we're creating sets. All right. Right. Well, let me try this. I didn't look at the answer too clearly, so I don't remember exactly what's going on. I wasn't trying to. Still trying to solve this, work my way out of it. So we are printing sets, and we have to use um, set notation. So we're going to say we're cross multiplying, so we're printing x and y sets, ordered pairs, in other words, such that, see here, we have x. Um, hmm. Anything times the first times 2. It should still be infinity to infinity. Yeah, let me see here. X, or I'm going to say X. X is undo such that is negative infinity is constant or equal to positive infinity. Actually, I don't know if you can do that. Putting them both in there. Yeah, I'm not going to get this one right. Okay. Let me see here. X and Y are members of reals, and Y is greater than or equal to 1. So, yeah. The correct answer is this. The order pairs of X and Y such that X and Y are members in the real set, and Y is greater than or equal to 1. All right. And let's figure out why it's saying that. That has to do with if I has naturals. Normally they would be populating this space here like this, but in this case we're talking about a real set. So X, according to this, and it would be anywhere. This is how you normally populate a natural set. Just a bunch of dots, but they're whole numbers. We're going to say this is the natural set. All right. But what we're saying here is X and Y are members of the real set. That's the full grid, and Y is greater than or equal to 1. So that means we have something like this. Let's see here. X ranges this way, Y ranges so X can go X can go this way. This is going to be 1. So that's 1. And then it would just be this block. That's what they're saying for the answer, and I'm trying to understand where I went wrong here. All right, let me think here. Contain the real set, Y is less than, greater than, or equal to 1. What about Y makes it? Okay. So I'm not sure how this whole cross multiplying the reals is working. I get that it's the plus 1 is why y is raised above 1. Let me see here. Let me look at an example. Okay. Definition 1.8. If a sub a equal to x such that x is a member of a sub a for at least one set a sub a with a containing I, and I is not an empty set. This is so an intersection. This is union. X such that a is a member of a sub a for every set a sub a with sorry, a sub a with a, and I'm being a member of I. Let me see here. This is where the brain melty stuff starts. All right. Note that. In this example, all sets A sub A are all subsets of the plane R2. Each A belongs to the index set IO2. X contains reals, and X ranges between 0 and 2, which is the set of all real numbers between 0 and 2 for each set A. Okay, so this is okay, so let's try A1. Take this set 1 0 0 1. Okay, let's see 1 1. For each set I, define A to be the set containing I. I'm just going to write this one out here and try to play with it a little bit. See if I can figure out what they did. Okay, let's see if I can modify it a little bit. 0 and 2 compared to ours was going to be I, comma, and it's going to be I, comma, I by maybe that would work. 1 times 2, 1. What about, but, this is a tough one. All right, let me see here. We are at, okay, well, anyway, I'm gonna say this is the correct answer, which is up here. I did not get that one correct exactly, but let me see if I can get the second part of it, the intersection. Okay, let's go back to this thing again. So that was fine, that was fine. Okay. Let's try another thing here. All right. I'm going to work on their examples a couple of times till I get it. Remember what I said, if you get lost, you can work your way out of it. This is how you do it. Anyway, this is the example. If you want on page 26, the book, you can download it. The link is in the description. It's free. Or buy the book. Also, I don't have any kickbacks from it. It's simply that it's Creative Commons. So, yeah. X this is, let me clarify this. That means such that X is a member of A sub A for at least one set A sub A, with A being A containing I. All right. And right now we're just worried about the union. This set with A for at least, and A is a set for every set A in some index, and I is not equal to the empty set. We're doing this. I is equal to O2, which is equal to X, or is a member of the real set such that 0 is less than or equal to X, which is X is greater than or equal to 0, less than or equal to 2. Okay. Which is the set of all real numbers between 0 and 2. Okay. So then we have, X is a member of the real set such that X ranges between 0 and 2. Now, how are we going to apply this with this set? For each number A containing I, define A to be at least the set. So then we're going to say A sub A is equal to A sub 2 times 0 A. So basically what we did was our set, we have 0. Notice that where the positions A occupy in the cross multiplication. That's important. So then let's say okay, so then we're going to say A is 1. A is equal to 1. So then we're going to say 1, 2, multiply 0, 1. And we're doing right now just the union, not the intersection. All right, so then this gives us the sets. Now let's use closed brackets. All right, 1, 0, 1, 1, 2, 0, 2, 1. All right. So now, if we graph this, all right. All right, we have. Actually, we're ranging between 0 and 2. So say 1, 2. Say 1, 2, 1, 2. Okay, 1, 0. X is 1, y is 0. 1, 1. Then we're going to say 2, x is 2, y is 0. 2, 1. Okay, and make sure this is correct. All right. Yeah. All right, let's try 2. So we're going to be stacking sets here and filling this in. We're going to form a shape. Hmm. All right. It's too big. We x is getting us into 0 and 4. Getting 0. 2 times 2 is 0. 2 times 2 is 4. And comma, we're getting 0, 4 again. And then wait a minute. It's a line. Okay. So let's just scratch 2 of these. Wait a minute. We're going to scratch the repetition. So it's x goes to 2y 0, 2 to 2. So now we've got this thing going on here. Got a line here. All right. And then we're going to say if they are 0, 0. Yeah, we can probably do that. Scratch the repetition. 0, 0. 2, 0. So this line right here. So what we're doing is we're creating this triangle, and what will happen is the more we fill in, they're all going to create this shape. There are going to be more boxes. Boxes shaped like this. Boxes shaped like this. And so forth. That's what's happening here. But the shape itself is a triangle, right triangle. Okay, so that was what's the example in 1.4, but how does that apply to us? Seven. Okay. So let me see here. Well, using the same principle. So we have, let me just erase this thing. Wait a minute. Maybe just rewrite it. So our set is going to be I, comma. So let's say A1, right? All right, we're going to try this again. All right, let's see if I can get this right. It's going to take me a few tries. I'm definitely stuck here. So, yeah, this is how you learn. Remember, this is a study stream. All right. What is that union of? Okay, well, you know what? Just write it as 1, I think. I need a sub. When I is 1, so that's going to be 1 times. See if I get this right. I think I just might get this right. Okay. 1 times 1 times 2 times 1. 2 comma 1. Okay. So the set that I would print would be okay. All right, let's try this. Okay, so all right, so the y is going to be x and y are members of the reals, whereas y is greater than or equal to 1. Reals times okay, I think I got it. Maybe I'm going the wrong direction on this. Simply put, if we're cross multiplying the reals, y has to be above 1 because when I say what the output of the y is, there's always a 1 being added to it, no matter what real you throw into it. So if it's the real is 3, then the x and y, I can't say for basically the y goes from 3 to a 4. If I say it's a -3, it becomes wait a minute, but it's greater than or equal to 1 instead of y plus 1. That's because they can't be negative. The i's range between only positive numbers. So they're members of the reals, but why wouldn't they be members of the naturals though? Because we're multiplying by the reals. That's why. Okay. It kind of makes sense to me now. We have, let me see here. We're cross multiplying by the reals, so that means, but i's are only naturals. So then the possible i's we can have, we can start at 1, 2, and then we can have, we're going to say 2, we're going to go to 2, 3, and so forth. Now, what happens is if we take a real, that's the set that we print out. We're going to cross multiply it by a real number. So this is where I'm messing this up. Okay, I'm getting somewhere. I am actually getting somewhere. Okay, let's take a real number. Let's say, I don't know. Let's say negative. All right. Negative 3. So then that's going to be negative 3 by, okay, which is equal to negative 3 comma negative 3, 1 comma perfect. Absolutely perfect. I understand now. Okay, and so basically, okay. It's not 4 things. What I messed up is I took the real and I split it up. I totally shouldn't have done this. Big mistake. But remember, you're cross multiplying by a single item at a time. The reals could have any number of items there. But so let's take 0.5, right? That's a real. We're going to multiply that by 1 comma 2 at the lowest point, because starting at the naturals, this is the lowest possible set. We can always go higher. And we're going to say the x can be, so it's going to be 0.5, 1 for the y. Notice that it's going to be 0.5, 2. If it was negative, then this would be negative, negative. So then, yeah, the x position, this one right here, or sorry, the y position, it's always going to start at 1. It'll only go up from there. Yeah. Now what'll happen is, so we have a grid here. The y's are going to go up by, can we get it to a half though? Let me see here. X and y are members of the reals. Y is x though. X obviously is a member of the reals. Why would y be a member of the reals? Or means maybe the set xy is members of the reals, contain real numbers. 1, 2, and I contain naturals. So yeah, I think that's what it is. All right. Yeah, I'm gonna probably revisit this question at some point. I kind of got it worked out in my head. So the only way I'm gonna know if I got it is if I can get the next one reasonably well. Let's see here. All right, so 7. The intersection of a real number cross multiplying I and I plus 1 Oh. Hold up. Maybe it was the maybe that's how. Hold on. No, this is X and Y. Seems to me. Hmm. Anyway, I really have to think about how the. Yeah, no, this is correct. No, I just went off a different tangent. Okay, getting back to what I was doing here. Where would they intersect? All right, let's just take. And I contains the natural set. So the increment by 1. All right, let's see here. We're going to go with. No, let's just pop 1. I equals 1. And we're going to say, so that means the set is going to be 1, comma 2. And then let's say I equals to 3, which is going to be 3, comma 4. Now, there's going to be some overlap, but they're all, let's see here. Now, if you multiply it by a real, let's just try by, I don't know, -5 by 1, comma 2, which is equal to -5, 1. Comma. Hold on. This goes back to the previous couple of chapters. We were multiplying reals by. Here we go. Here we go. Page 10. R by, yeah, that's fine. Okay, well, let's see here. Well, let's just keep ordering pairs, see what happens, what we get out of this. -5, 1. -5, 2. Mm-hmm. Hmm. All right. Let me have a stab at this thing. Let's see. Here we have. Reals times. Where would they all intersect? They would all have to appear on that. It seems to me there would be no intersection, except maybe. Yeah, this is the hardest chapter by far. It would have to appear in every set. It doesn't give us a upper lower bound. I'm thinking this is going to be... I don't think there's any overlap. Let's find out. Thank God. I got that right. Okay. Getting to somewhere. That's right. Book agrees. All right. All right. Let's try 9. A union of X containing the power set of the naturals Okay, the set X. So the power set of the naturals, it would be the empty set. No. It starts at 1. So the power set would be like this. Let's work out P to the N first. X is a member of P to the N. Power set of the naturals is equal to empty set 1, 2, 3, N, small n. So it's going to be the empty set 1, and these are singletons, and then it'll be doubletons, tripletons, blah, 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 just keep growing. So X contains the power of the natural sets. How to even answer this? So I would think that it would just be P to the N. If X is a member of P to the N, and P to the N just contains power sets and natural sets, I would have to say yeah, unfortunately, there's a dearth of examples for this to look at, so it makes it hard to apply, because they didn't even show an example of applying a power set to this stuff. I think it should be just a power set to the N, and if it's a union, it would be all of them. Or N set N. Oh, this would be the set of the set N. I think that's how we would do this. No, it was close. Don't need to do the set of the set N, just N. Okay, I wasn't that far off. Okay, so that's right. It's basically the power set of the natural set would be the singletons, doubletons, tripletons, so forth. Would keep going on and on and on. But essentially, what you're doing is you're recreating the natural set. So sort of you're reboxing it to where by the end it would be the whole natural set. The final box would contain the natural set. And since that's actually a pretty good explanation. I think, at least for me. The final box will contain a natural set. This is a union. So in this case, it doesn't matter. It's just a natural set. So the intersection, where would they all intersect? They wouldn't. There would be no intersection because if x the power set of n, it would be each of these power sets. They all of these would have to intersect within each other. Basically, is what it's asking. If this is intersection, I would say that there's no intersection, because how would the singletons intersect with each other? They don't. So the set X, the set of the singletons, because each of these is a new set. You see what I'm saying? The curly braces means to set. So I think there is no intersection if we are talking for the power set of the set N. Okay, I'm going to say no. And the book agrees, fortunately. Okay, good. Oh boy, this is a hard chapter. Yeah, but I got that one right. So this kind of a thing, I know that it's just a little mind melting. This is like, if this is thrown in on a test, this is the kind of stuff that's very easy to get wrong, but it's fine. Once we get through this, there's going to be a lot that important stuff will keep coming back and back and back, and then we end up reusing it. So it's, even if it's like we're shaky, like a newborn horse on a frozen pond, then it will still be fine. There we go. Okay. 11. Is it a member of the set always true for any collection of sets A sub A with index set I? Is index sub I... It's Russell's paradox. Is it always true? By the Zermelo-Fraenkel set theory axioms, I believe it's true. Hang on a minute. Where is the... Wait a minute. No. Okay. Roll that back. This isn't a set within a set. Well, it kind of is, but this is the intersection of sets with an index I with a set of A sub A. Are they a member of, or are they a subset of the union? Seems like it's true, because if there's an intersection, it would be in the union. Let's say yes. Yes. Any intersection is also found in the union. Okay. That's what I think is right. Unless there's some like tricky set. Okay. So is the subset of A sub A such that with an index I, so then is that a member or a subset of a union of the same A sub A with an index I? It seems to me it would have to be because anything that's found in a union, anything that's found in a intersection can be found in the union. So, yes, this is always true. Oh man, I am working hard for these. Okay. But hey, the greatest reward, the greatest reward for learning math is being able to do even more advanced math. Remember that. And it's a never ending quest. There's always much more advanced math to learn, to do. So it's a way of life, really. I mean, if you get tired of not being super rich, then just go to Wall Street. I'll fix that for you. Believe me, it's much easier to go to Wall Street if you are a programmer mathematician than if you are a trader who has to learn mathematics and programming. You know, it's much easier to teach a mathematician trading techniques than it is for a trader to become a mathematician. At least, obviously, like I was a dude bro crypto trader back when everyone was during COVID, and it was good for me for a while. Not gonna talk about any of that because it's just basically hot garbage. Um, but it's no different than just like lottery tickets and whatever. But what I'm trying to say is that if you have the right kind of instinct and you happen to be a mathematician, you could easily go to Wall Street and easily, not like super easily, but I'm not a mathematician, but a mathematician with a trader's instinct could easily become a trader. A trader with a mathematician's instinct will have to work a very long time to become a mathematician. So you see how that works? Anyway, so let's see here. Again, I'm not a mathematician, I'm a landscaper and handyman. So this is I'm a student at Westchester University for a class I didn't pass. So this is my study stream. All right, if set J is not empty and J is a subset of I, does it follow? This is closer to proofy kind of questions. We're not writing proofs yet, but for as hard as this chapter has been, this is nothing compared to when we start doing proofs. Okay, subset. Okay, if set J is not empty and J is a subset of I, does it follow that union of A sub J is a member of union A sub A being a member of I? It seems to be. And except I missed this. A sub A. I would say yes, this would make sense because if J is a subset of I, so let's just give an example. So I, let's say here is going to be 1, 2, 3, 4. Okay. And J is a subset of it. Okay, that's fine. So then does it follow that union of A sub A is going to be a subset of union A sub A? I would say yes. For the intersection, it might not, because for the intersection, because the J's it'd have to contain them all. Okay, hold on. Let's think about this for a minute. What about so does it follow that union of A sub A? Let me go back here. Definition 1.8. If A sub A is a set for every A in the same index, set I is not empty. Okay. Then the union of for at least one set A with union A contain or X contains A for, so yes. Wait a minute, for at least one set X. So that means there's a set X for all such that the set X is contains A sub A for at least one set A sub A with A containing I, because I is not empty. I think both are yes. I'll put it this way: if something that is a smaller piece of a larger whole, but these are sets, I would think that they would all be part of it. In this case, the I is the index. So the index itself is not the set. It simply means taking the first set, the second set, the third set, and the fourth set. That's the index. In this case, J is also an index. It takes 2 and 3. Sets 2, sets 3. So presumably, if there's an intersection, then yeah, yes, for every set, because by definition, an intersection has to be found in every set. Yeah. And you have to explain this, so we're going to say hope you enjoy having your brain melted. All right. J A sub A. Okay. Yeah, can't write. Yes. By 1.8. See that for every J, which is a subset of I, comma, the intersections in I will be found in J. I would say yes. So these are indices that we're talking about. Okay, what about, does it follow that? Yeah, because it's a union. Yes, because I would say both are yes. Yes. Wrong word. Okay. This is what I think. Let's see what the book says. First is true, the second is false. So basically, well, the first one's kind of easier in a sense because when you have a union, it's very easy to be a part of the union. So if you know something exists, the second carries over. So second part is false. Why is it false? Okay. Let's correct this. Okay. Clean that up a little bit. So, this part, now we're going to draw a line here and separate the two a little bit. If the intersection of A sub A is it part of the intersection of A containing J? Well, I would think it should be, because I'm kind of going off of 11. Is the intersection of A... That's what I was saying. That's what's throwing me off. The way they answered... I answered 11 correctly. And this is playing off the same thing, but the difference is that J... Oh... Because this is, it's a little thing. It's a tiny little thing, but that's what threw me off. Okay. Because J is a subset of I does not mean that see here, I is a subset of J. There. So that was the issue that I'm seeing, because J is a subset of I, but in the bottom statement, and that would I kind of mixed this up. I thought this continued with J as a subset of I, which, watch, I wonder if I wrote it wrong. Let me see here. Wait a minute. J is a subset of I. What about intersection of... Oh, I even wrote it wrong. Wow, well, congratulations. All right. So I answered correctly for something I wrote incorrectly. Let's try to write it correctly and answer it correctly. That would be something. Let's do that. Okay. First, let's fix this. Okay. J I. Okay. So if J is a subset of I, J is a part of a member. The index J is a subset of the index I. All right. What about, is the intersection of the A sub A part of the intersection of A sub A? So in other words, is the indices are subsets, like I said earlier, but are the sets also intersected? Well, I need to find an example where there is no intersection in different sets. If there's an intersection, then it would carry across, yeah? J is not empty, and J is a member of index I. All right, well, let's write some, so we have indices. Let's write some sets. Okay, let's say A sub 1 is equal to, just take them, they might have actually given, okay, so A sub 1 is going to be -1, 0, 1. A sub 2, let's try here, -2, 0, 2. A sub 3, -2, 0, 4. Okay. All right. So, and one more time. A sub 4. Taking, right. A sub 4 is just going to be 0. So that's, so if you take the index J, that would be 1 through, sorry. All right. This is, I'm going to change this around a little bit. So which one is the bigger index here? The main one is I. So I is going to contain all 4 of them. And then if we're going to say union of A sub A and A contains J intersection. So that means which is equal to the 0. That's the only intersection. Now, what if J, which is a part of the same index, happens to contain 2 and 3? So in other words, we're taking these two right here, yeah? So then that means that the intersection of A containing, I need to learn to double check my work. There we go. This is I. J would actually have a larger, even though it's a this is what I was trying to prove. I finally got it. You got to write math more. You know, you got to put pen to paper. So even though J is a subset of I, and both are indices, and I listed our indices right here. So this right here, this is the index of J, sorry, of I, and J is a subset of it, J only containing 2 and 3. So in that case, even though it's a smaller index and it's a subset of I, the intersection actually happens to be bigger because the way I structured it, by throwing in A4 and making that only contain the number 0, then that restricted the intersection to 0 versus in A containing the index I versus A containing the index J is, even though it's a smaller index, it has a larger subset. Yes. Q, E, D. There we go. Okay. So, there we go. Okay. So, let me see here. And I need to, actually, before I do my QED mic drop, which I think looks pretty cool, but I'm actually going to write this out because I don't look like such a madman. All right. Okay, not going to lie. I'm not claiming to be sane. I'm just saying that I want to at least appear legible. So here we go. In this example, okay. I'm gonna move this. A minute. I think you can move. Okay. 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 Quado et demonstratum. Thus it has been demonstrated. All right. Well, that's it for the chapter. We finished it on a bang, even though there were some rough moments. I gotta tell you. Oh man. But you gotta wrestle with this. This is what math is about. Okay. The night is still young, and I divide up each stream into by chapter, so that anyone who wants to go back and study with me can go back and look. Let me see what we have for 2.1. I just want to see if it's worth jumping into it right now. Okay. All right. Yeah, this is great. Let's do 2.1 next. I might even blow through most of 2 today. I don't know how I feel. Oh, no. It goes to 2.7. That's not too bad. Okay. We're going to drop some truth bombs here, or more specifically, truth tables. Express. Oh, this is going to be so much fun. All right. Okay, shutting down the stream. Just give me a few minutes. We're going to restart it right back up. Don't go anywhere. All right, and ending stream.